So let's talk about PCBs and where they are today. So in essence, to make a PCB, you can decide on how many layers you need from design, but you basically have three main elements, or the basics of the PCB. So you've got the core materials. So if you look at the pictures, it's the one top left. A core material is basically, you could do that as a two-layer board. So this starts the same, the process is exactly the same. You print on one layer, you print on the other side, and you can do that. So you might have 2 layers, you might have 10 layers, you might have 50. It doesn't matter. But that core material clearly would need to be thinner the more layers that you put into a PCB. So in terms of thicknesses of core material, you can have a thickness down to 1 mil or 25 microns in thickness. So that's for not many guys I can see here, but if you've got hair on your head, that's kind of like half of the hair width that you would have. And you imagine holding that as a big sheet of material, because manufacturing, what you want to do is you want to get as many PCBs, certainly in volume, onto a panel that you can do. So you've got these 18-inch by 24 sort of general size sheets of material at 25 microns thick, at the smallest case that you have to try and carry around. The traces themselves on these sheets can go down to 25, 50 micron. Most everyday PCB designs you see these days, for most products, tend to have lines of around about 75 to 100 microns. And pad sizes generally about 400 to 500 microns. But the way that it works is you have to put these, if we talk multi-layer, you'd have each core separate. So you'd have layer 2 and 3 on one core, 4 and 5 on another, 5 and 6 on the other, and so on as you go down the layers. Once all those layers, inner layers, I'll call them, are put together, they've all got to be bonded together. Okay, now you can imagine with these fine geometries, some of the machinery needed today to get that to work, so all aligns up together, is very difficult. But in essence, the way that things are bonded together is you've got each core material, either side has what we call a pre-preg or a B stage, which is the top right picture. And then literally the outer layers, you just put a layer of foil, copper foil, on the top, on the bottom. You bond it together using a heat press, okay, and then you progress further on. But that's effectively how a modern day PCB is made, as we talk today. This I've put Mr. Boring Man on the left. I've got to be a bit comical about this. Basically, what you've got is these are, I've printed out the processes needed. There's more to each of these processes that go on, but this basically will give you an overview of what it takes to build a multi-layer PCB. So it could be a 4-layer because it's more than 2, or it could be up to 50 or 60, depending on what you've got. I won't go through each of these, but I will give an overview of some of the things that you would do. So basically, the first stage is inner layer. It's obviously shortened to IL here. But what you've got is you've got to do the material itself has to be treated first. So in essence, it's cleaned. It needs to be cleaned before it goes into the process. If you imagine obviously a thumbprint on the copper, or at this stage, at the early stage, or just a dirty thumbprint on copper, that might end up being a load of different tracks on the PCB if you don't wash all that off at the start. So everybody in the processing is wearing gloves. Most of the processing is done by robots. There's not much human intervention in some of the internal processes now. So a lot of that is done first. So you do a pre-treatment, so there's a clean. You laminate the PCB, so you put a film on the board itself, ready for a copper pattern to be added or to be imaged onto it. So it's obviously imaged. What happens with the image? In essence, you've got a light source, which basically you have a film which shows the copper tracks and the pads and what goes on. That is put onto this film. The light goes through it and it hardens off the copper area. So when you etch away the resist you don't want that leaves you with these traces. So that's the basic principle of that stage. You've then got an optical inspection. So in essence, what this does, if you can imagine, let's say you've got 100 micron traces, 100 micron trace and gap going through all these layers. There is no way you are going to sit there with your eyes and physically see there's no problem. So the AOI, what that does is it physically scans the PCB at this stage that's done. So these are copper tracks. It scans them versus a data set So the original data that you've got for that board, making sure they match. If they don't match, generally what happens these days, they get slung out, slung in the bin, and start again. Once that's done, and you've basically got all of your inner layer cores together, ready to go, it goes through a process of oxide. Now, oxide is basically what it does. It roughens the surface of the copper. So when you press it and bond it all together, that prepreg I spoke to you about earlier, it actually bonds and bites into that copper. That's what it's for. That process these days is becoming more of an issue, because the rougher the copper, the worse the signal on the traces that you've got. The traces have got to carry a lot more data now than they've done ever in the past. So in the PCB world, we're having to find other ways in which we can introduce new oxide treatments to effectively make that not so rough. And effectively what that does, the signal that goes through that trace then becomes a lot smoother. Okay, as I said earlier, it's all pressed together. There's a drill process, X-ray drill. What that does, it makes sure that the layers, all internal, are all lined up together before it takes it to the next stage. Okay, so let's go through the next one. This then goes to an outer layer process. So you've basically got on the internal layers, on the manufacturing panel, there's a load of fiducial marks or images that you can find with that X-ray. What the X-ray does, it can literally go from layer to layer to layer to layer to make sure that fiducial pad is exactly the same position, or as very close as possible, through all the layers. Once that machine is happy that's correct, it then drills holes, tooling holes in the panel to say that's your start position of what you want to do. Once that's done, those tooling holes are actually located as pins on a proper drilling machine. So then that goes onto the drilling machine, and that drilling machine will then go ahead and drill through all of those pads, okay, and the ones it needs to. So you've basically got all your drill hole positions done. Now, drilling these days, basically, you can have drill hole sizes generally from anything from 100 microns or 0.1 of a millimeter upwards. But again, the industry standard tends to be around about 200 micron or 250 as a what we call a via size, so a connecting via that you put through the board. Clearly, you're going to have more drills on there for components. They'll need to be slightly bigger, but effectively, it's the same process. So that's the next stage of drill. After drill, the board is then having to be cleaned again, because if you can imagine what would happen to a drill going through fiberglass, it shears all of the glass strands inside that hole. And if you were to put that under a microscope, what you'd see is you could see all the splits where the holes of the glass bundles, if you will, have been fractured and obviously damaged. So we have to go through another cleaning process then, which basically makes that nice and smooth. And after that, you then go through a plating process. So you put a very, very thin layer of plating on the whole board. So everything again becomes metallized. And you then go through the same process again, as I said earlier, where you've basically got an image put on. So this is the outer layer image. Okay, and then what you have is you've got the copper that goes on the outer layers, and obviously in through the holes as well. Your connection at this stage is already done. Again, similar process of an optical inspection to make sure everything's okay. You then put the solder mask, so the green mask, goes over to protect the tracks from obviously its final placement where it's going to go. Any component marking, so silk screen as it's called, or you can do it by even a printer now, basically. You can put that on if it's needed. And then you do what would be the final finish. So the final finish would be, if you looked at a bare PCB that's complete, you will have different ones. You can see it looks like a silver color, a gold color, could just be like copper color. Each of those is its own finish that you can put onto that board. The reason the surface finish is it's needed so that when you put the components on, the components would solder onto that PCB. So that the purpose of the finish is purely as a barrier. So when you solder components on, that finish will effectively melt and give a good adhesion between the component and the PCB. So all in all, as I said in the right there, there's 62 processes. So that's a lot of work needed to make a multi-layer PCB. Okay, a bit more complex. I won't go into this one. Don't worry, I'm not going to bore everybody to death with this one. But this talks about the evolution of servers and of network. And what you can see is in essence, from what you would understand, is the speed of which is needed for that PCB to work has gone up and up and up and up. You know, you need to make sure that how do we do that? How do we make sure this PCB can carry these kind of values that we need to make this board work? So in essence, you could say, if we pick on, let's just pick on network. So in the early 2000s, you know, network only needed a bandwidth of 10 megabits per second. But we're now talking about today's PCBs, they're up to anything from 25 gigabits up to 100 and more. So these PCBs, the bare board, not the components, the bare PCBs somehow have to carry that level of speed of a requirement from the components. So what we're able to do is we've got, first of all, the laminate itself. The laminate itself, there's different blends of epoxy, which basically can carry different signal speed or work better under load. So you've got the various different ones. So those in red, the dielectric, you can see where it's been at the start, high loss FR4, we're now getting it to the much more ultra low loss, extreme low loss, different types of laminate that we can use, we have at our disposal to make that work. The other important point of that as well is also the foil itself. You know, you think if you look at a foil, a layer of foil, or a copper foil, there is a big difference between what would be a standard foil, which to hand is very smooth, nothing wrong with it at all. So actually what we need nowadays to some that's got almost completely flat. Again, looking at the microscope, you would see a standard foil is like, it's peaks and troughs, you'd see it doing this. But you know, as the foil has evolved and it's needed, you'll find it becomes flatter and flatter and flatter. Okay, you then got different reinforcements of that resin system. So the core I talk about, the way it's made up, or has been made up for years, is basically you've got interwoven glass bundles together, so it's glass fabric. And then you apply the resin system, so it could be a basic resin, could be an extremely low loss resin. It goes into pretty much the same types of glass bundles that you would have. That in itself is so you've got that glass, but that glass as well can be can differ to make that so you don't have too much difference between them. So that's, we won't go too much into that one anyway, but I can talk about a bit more about that a bit later. Okay, so this basically is an example of a PCB made by my firm. It's believe it or not, it's a relatively basic PCB, but it gives you an idea of what some of the requirements are, what you can expect to see on these boards. So I'm going to go through some of this stuff. So board thickness, 189 mils in thickness. Material is a given material that is needed to carry the signal speed within this board. It's a 40 total layers. And the panel size you see there is one that we've used to manufacture the board. So we've had to use a 42-inch. So this is probably going to be a backplane of sorts. The aspect ratio, what that is, that basically means is what is the diameter of the hole versus the plating that you can get through that hole. You know, whereas before, years ago, you'd have to have a very large hole to get the copper solution through and to stick where it needs to. These days, you know, you can have very, very small holes on very thick dielectric, which is obviously a need of the PCB itself. Core thickness, 2 mils, so 50 microns. Tracking gap, as I said earlier, we're down to around about 100 on this one. Okay, we'll leave that one now. Okay, this one just talks about, as well as just the basics I discussed, this talks about some of the technologies that is into PCBs as we speak today. So I'll try and give a bit more of an overview on this. So back drill. In essence, you may say you've got a trace that travels from layer 1, let's say, to layer 6 of a 10-layer PCB. What you don't want to do is to have the current flowing through that board that then carries on through the full copper of that via. So in essence, if it went from layer 1 to layer 10, you're wasting all that space. You don't need that. That would give an interference, if you will, to the actual trace they want. They only want to see layer 1, 2, 3, 4, 5, 6, follow that trace and terminate. They don't want to see what's below that. So what back drilling does, it actually, you can use a slightly larger hole to actually drill through the copper hole that's there to take away the barrel of the hole, so you're stopping at a given layer. So if we were going from layer 1 to 6 as our copper, you can see we start from layer 10, we back drill, we go to as close as possible to layer 6, so we make sure that signal is as clear as possible and doesn't get interfered with. You then got what we call HDI, high density interconnect. You've got +2 and +3. This again is again it's quite an old technology, but it's used a lot more now. This is where a conventional hole size has become too big, and it's not. We need to find another way of doing it. What this does, it actually drills the hole with a laser. So the laser would basically ablate the copper on the surface layer. It cuts through the dielectric and it stops on the copper layer below. And with that, you basically get a very, very clean signal. So you do one from layer 1 to 2, and the 2+ you've got from 2 to 3, and 3+ it does the same, and so on. Now you can basically imagine that some of the BGA chips that you can buy these days, the pitch is getting smaller and smaller. So a conventional hole and trying to get all the connections you need becomes almost impossible. So what they do is they actually drill these holes, and they stack them on top of each other. So you basically you can put a 75 micron hole from layer 1 to 2, 2 to 3, 3 to 4, and so on, and stack these up and up and up through the whole of the dielectric. If you look at the 6 layer, any layer on that one, you can see what's happened there is they've had to do a 75 micron hole on each layer. What you do is you drill that hole, you fill it with copper, you then do the next layer, and you repeat that process over and over. So it's almost a through hole. It's almost a standard via hole, but you can't do that with a mechanical drill. It's just too small. So that's some of the things we do. Multi-net via is where you get clever and you try to break connections at certain points. So you get very clean signals. Depth control is where you may have seen, if you've seen some bare PCBs, you've got what we call the rigid PCB, which is a standard. You see the green mask, it's standard, quite thick PCB. And then you can get flexible PCBs, which are a very, like almost a brown paper tape, you see it, where you see those. What this does, depth control, is where we would literally cut into the rigid PCB to a point where it becomes so thin that you can bend it. Now you couldn't do it too often because the material itself it contains glass strands, and it would eventually snap and break. But for a one-time bend, if you had a component or a board you wanted to put into a certain housing that needed part of it bent over, this is what that's for. So you can do that. Again, this looks at some of the things we talked about a wee while ago. So this looks at a cross section of a multi-layer PCB, and you can see there that you've got it shows some very fine lines. You can see how the hole geometries work. There's a through hole there. You've got some back drill going. You've got buried vias, where vias are basically placed during the process. So the buried via, for example, if you had a 10-layer board and you wanted to do from layer 4 to layer 6 first, you would bond layer 4 and 6 together first. You drill it as a through hole, standard through hole. You plate it, and then you bond on the other layers thereafter as you go through. So that's just some of the technologies that you would see on a given board. This one talks about heat disbursement, how we can take care of heat. So components these days, they demand a lot of heat, but some of them are very in very selective areas. So you can do lots of different things. You can basically, in this case, what we've got is we've got some very heavy copper, and we use that as the thermal path, and we can drill into that copper just with the vias that need to use that thermal requirement. So this might be, it usually it's all in ounces. So a standard copper would be a 1/2 ounce or a 1 ounce, which is 1/2 ounce is 70 microns, 1 ounce is 35. Anything above 2 ounce we deem in the trade as heavy copper. So this could be 2, 4, 5, 6 ounce copper. That could be put into the boards as we bond, as we want to bond through, and then we can drill into it as we need and use that as the thermal path. So that's one way of doing that. This picture basically is again, it's a selective area where You've got standard PCB material on the left. You've got an RO4350B, which is from a company called Rogers, which is a different dielectric material needed for this given component. And then you can see in the bottom there's a coin bonded into that as well. So we can call them coin. It's a slug of copper. So basically, you could put where a component needs a lot of heat disbursement, but it's very selective. But it needs also a specific dielectric material. You can put this in selective areas. So you'll see that going on PCBs as well. Looking about how the PCB itself works. Now, one of the things we have to do is we have to, first of all, choose the right laminate, the right copper, and choose the right process to make sure that it will meet what the customer need is. But generally, you can have things like controlled impedance, where we need to make sure that the traces are controlled to a point where we can say that when the component is placed, they're going to have consistent value or frequency as it goes through. So we have to, generally what happens is designers do this. They would basically say, they would look and model to say what trace width needs to be, what the space needs to be, what the dielectric to the next copper layer needs to be. All of this needs to be put in, and the designer would physically put that onto the board. As a manufacturer, we have these same tools, and we have to check to make sure that their design value meets what would happen to manufacture. And what tends to happen is that you tend to end up calling customers to say, your track of 100 microns, we want to make it, I don't know, 105, 110 to reach a nominal value of impedance that you're after. That normally gets agreed, and we go ahead and manufacture based on that. But bearing in mind, you're going to have in volume manufacturing these days, you know, a company, a very large OEM would want to use anything between 2 and 4 manufacturers. So each manufacturer, because of their processing, will have a slight variation. So that's why these tools are used, just so everybody can be as close as possible what to the design or the designer requirement is. I talked earlier about how a PCB composite is made up. Basically what you've got is it's made of glass bundles, resin. Now these glass bundles you can get in different pitches, you can get slightly different thicknesses, but each one would have a very specific requirement for any given PCB. What you see is these pictures, they show the top ones, they show a cross section where they cut through the PCB, and where there's a difference between the resin system and the glass itself, that can have an impact on the workings and the signal that you see from a PCB. If you look at the left picture, for example, what you see is the two, I don't know if you can see, if you see the layers, you've got 2 copper layers above and below, and then there's 2 traces in the middle. What the oval shapes are is just the cut of the glass bundles. And you can see that trace. One of them is below the glass and above the glass, and the other one has just got pure resin from the copper above and the copper below. So that can have an effect on how the PCB itself works. So there's been a lot of advancements in the actual resin system and glass system these days as well to improve that. A lot of the glass systems now can be done as flat, so that there's no window of dielectric. You purely be glass above and glass below. This will change. You will find that the way the laminate is constructed, I think glass will be removed, and we'll be left with a filler or a composite with the resin, which matches the same performance level, if you will, as it goes through. Okay, this is, I talked earlier about technologies of PCB. So you've basically got, in the past, you've had through-hole changed to microvia. So you had just laser via from any layer to another layer. This is just another technology that's coming to the market now, where effectively you don't use a hole. You basically you route a slot, okay, and that slot then gets broken down, so you end up with pillars of copper rather than a through hole, rather than a round hole. You've got a pillar of copper, which is a very, very good way of space saving on a PCB. Our company are working with this, as are others now, and we will see more of this in the future. In terms of factories, obviously, as I said earlier, I work for a firm in China, There's a lot more automation goes on with factories. It used to be, there always used to be a case of there was, you know, one guy, one girl per machine, a lot of people. But that in itself, you've got two things there. First of all, obviously that's a lot of people you've got to employ, and it gets very expensive. But more importantly, what you find is the, as I said earlier, the actual PCB as they start. So the first few layers of maybe 25, 50 microns in thickness. If you were to carry that as a panel, just with your hands from one place to another, the likelihood is that you would make that bend or break, or you'd put a kink in the metal, and if that was a trace, it would break in the final board. It wouldn't work. So what this robotic stuff does, it physically, most of it is like suction cups. It picks up the panel in lots of different areas. So it doesn't get, there's no chance it can get broken or buckled or bent or anything like that. So this would pick this up, literally carry it from one place to another as it goes through. This is just one part. This is actually part of the inner layer process here. But there's a lot more where you've got physical robots literally carrying PCBs in a near finished form from one place to another, taking out any indication or any need for human intervention. This is a picture of a drilling machines. So a drill shop, we call these. Again, there used to be one person per machine, but because of the automation there now, this automation built into these machines, you don't need it. One guy can do 4 machines now, which is a lot better. But in essence, these drill machines, just for a view of scale, each machine has 4 to 6 beds that they can put the same PCBs on. You can stack the PCBs 3 or 4 high, and they all go ahead and drill the holes as you go through. But if you walk into these places in China, you know, a UK manufacturing prototype might have 5 or 6 machines. These are, you know, the size of football pitches. It's absolutely immense, some of the work they need to do to get these out in the thousands of boards. So yeah, when we're in high volumes, these things are needed. Okay, last few slides then. This is basically, we're talking about 3D printing earlier. There's also now quite new to market 3D printing of PCBs. This company I've followed for a while. They're happy for me to show these slides. I've spoken to them about it. Effectively, what they want to do is that they're promoting a 3D printing service of PCBs. Now, this is where things start to get exciting with PCBs for future. As it stands at the moment, they have a resin system for the dielectric, and they have a paste for the traces, if you will. So it's a conductive paste, obviously. It cannot carry the same signal speeds and as such compared to PCBs at present, but it will evolve very, very quickly. You'll find that these PCBs can be printed generally in about 24 hours to build up as it goes through. What Nano Dimension did is they first started out with offering this service as a way to match, if you will, the UK manufacturers, actually worldwide, prototype service. So they could build any PCB within 24 hours. That's what the service offered. So they're trying to sell the machines to people that want to build these PCBs. Now, the cost of the machine is very expensive. Cost of the ink and the dielectric is very expensive, but it's in its infancy, and it will change. One of the things they did initially is that they marketed it to try and, as I say, to take on the standard PCB community. But what became apparent very quickly is the fact that, you know, you don't have to do a 2D PCB with a 3D printer. You don't need holes. You don't need to do that. You know, you don't need to do it on a 2D version. So literally layer by layer by layer. You can print whatever you like. You can do it however you want. So this is what this shows. As it stands presently, these boards can be assembled. There is a few issues around that which are being put right now. But you can assemble them. You can do what you need to do. And effectively, if you've got a requirement of something different on a PCB, you can do whatever you want to do. What will happen with this is, in 20 years' time, I have every, I'm an engineer. I know in 20 years' time, all of the processing of PCBs that is there today in these great fabrication shops, I don't think it'll be there anymore. They'll be just printers. They'll become cost effective. You'll be able to receive a design, I don't know, from Amazon if you want. You can get it from wherever you need, whatever your PCB need might be. And you sit there at home and you go, right, print, click a button, off you go. You don't need anything else. What's evolved with this now is what can be done with these printers, what can be done with the PCB. So these are just a few examples of some of those you can see. This one is the way it's done. You can't, if you look at this presentation later, I think Joel could send it through. In essence, what you've got here, there's a dielectric. You can see the ring through the center. There's actually a trace in the middle of that as well, which is effectively in air. So it's printed with no dielectric material around it. So you don't have to do that. You can just literally hang it within the center of the board. This is cut through, but it would be attached somewhere, attached obviously at another end. But in effect, you could just leave this literally right in the middle. This one is just, again, an example of some of the stuff they've done. I think there's some more that are slightly better. Do look at the Nano Dimension. You can see I've put them in the bottom left. Look at their website. Look at the stuff they do. There's some very, very interesting PCBs. This one is again just challenging the standard PCB concept of, everything needs to be done on the surface of the board. You can see here that they've actually 3D printed the traces to the sides of the board, and that they've put the resistor or capacitor actually on the side itself. So there's lots of things you can do to save space, but also challenge what the standard PCB methods are today. Sorry, this is fuzzy, but again, it's basically what this does. It's not 2D, so the trace can go anywhere. In this case, the trace goes from the top side to the bottom side by actually printing on the side of the board as well. So something some of it's partly doable in standard processing, but not not so much these days. And this one, which I think is the final one, again, it's still considering a hole. You can see that the holes around the outside. So that I think will eventually phase out and be gone with. But in essence, what they've got here, they've got a multi-dimensional potential of putting chips. So you can put a chip here, so 1, 2, 3 different chips in the same position on that board. So it's just challenging what's possible within standard PCB production. In essence, with this, what will evolve is you'll find that the 2D, which is still there to a point, vision of PCBs will go, and you'll be able to put a trace on on an angle, you can make it literally you can do it from anything you can think that would happen as a 3D. You can do it, put it together, and it will have a big influence on PCBs and what's possible for future. So there's a few people out there now doing 3D printing with electronics, but these guys are the ones that I'm certainly watching. I think they're the ones that will. They're certainly class leading now, in my view, and I believe as things evolve, these will become the PCB production. Will become the PCB production future. It needs people and engineers now to rethink construction of boards or rethink designs and what's needed. And once that's done, once these guys they get better with the different dielectrics or dielectric materials, or the better with the dielectric that they're running with, it's going to become standard, and that will be the case. So that